So here's problem number 17. Let's go with the facts that we have. We are told that f of 2 is equal to 3. Tell me more about that for just a second. Yeah, Evan?
That means whatever function f happens to be, that at the point where x equals 2, that your corresponding y point is 3.
It goes to that point.
Yes.
Okay, great. It says that y prime of 2 is equal to 5. Interpret that, please,
That's the slope at that point.
at that point. 1, 2, 3, 4, 5. So the slope is something like that at that point. It may not be going that far, but something like that's going on there. All right? Find the equation of the tangent line. Okay, let's go through this idea of tangent line. Tangent line. Typically we use the slope point form, and we need to know what the slope of the line is in order to find the tangent line. Wait, Charlie, what did you just say this was?
That's the slope of the line at that point.
Edmund, what did you say this was?
That was the point.
There's the tangent line.
But wait.
Oh, so what were they doing? Were they testing you whether you could do a tangent line? No, they were testing you. Do you understand the notation and what the notation means? This means slope at x equal 2, and of course this means 2, 3 is a point on the graph. Now the other part of the equation, the other part is what's the normal?
Well, that's the
So this is,
perpendicular.
right. So this one's the tangent, and so the normal. How's it change? Negative 1/5, because the normal is going to be the negative reciprocal, but the point remains the same. So there's your normal. Is that okay? We good?
Yeah.
Okay. All right. That's number 17.
Mr. Fedor,
Yeah.
to find the tangent and the normal line,
Mm-hmm.
I did y equals mx plus b. I put 5 in for m, 2 in for x, 3 in for y, and I solved for b, and it worked out the same way for both the tangent and the normal. Is that like?
If I distribute that 5 over there, I get 5x minus 10 plus 3, which is 5x minus 7. So this equation is perfectly fine. The equation y is equal to 5x minus 7 is perfectly fine. They're equivalent answers. They represent the same number, same points. They're just fine.
Okay.
My only worry is that, or not worry, I hope that you feel comfortable in both of those. Because if it's a multiple choice question, there's no guarantee it's going to give you in point slope form or in slope intercept form. And you got to be willing to know that both of them are acceptable and both of them are equivalent. Alrighty, 17, going once, going twice. Next, 29. 25 first, sure. 25. Okay. 25. This is the which function is its own derivative question. And I would like to do this question by looking at and going on the calculator and doing the graphs. And let's start with the first one, which is sine x its own derivative? Stop that. Window, I want the trig window, 7. So it's a little bit bigger. All right. So what do we mean it's its own derivative? Well, we know that given a graph, we should be able to do a rough graph of what the derivative function looks like. Is that the right one? Is it sign? Yeah. So I would like to know, given this graph, what does the derivative function look like? Here's some simple hints to try to figure that out. Wherever there's a horizontal tangent, the derivative function is 0, because horizontal lines have 0 slope. So the derivative function, which I am doing in red, is going to be 0 here, 0 here, 0 here, and 0 there. Wherever there's a horizontal tangent, the derivative function has a y value of 0. Secondly, wherever a function is decreasing, the derivative function is negative. So between these two dots, I see a decreasing function. I'm going to say that the derivative function is going to be negative between those two spots. Between these two horizontal tangents, the original function is increasing, so the derivative function is positive. Between here, it's got to go back down to 0. Between these two spots, the derivative function is decreased, or the function is decreasing, so the derivative function is negative. And see it increasing, I think it increases there, so it's positive. This function is increasing, so the derivative function is positive there. So the red line would represent the derivative function to the black line's original function. Yeah?
So then would you say that cosine of x is the derivative function of sine x?
The derivative with respect to x of sine x does end up equaling cosine x. Later, we're going to prove that. All right? But right now, visually, it jumped out at you, didn't it?
Yeah.
That it was cosine?
That it was cosine. So the derivative of the sine function is the cosine function. So there's one down. But is sine its own derivative? Is the derivative of sine sine?
No.
No. Okay. So we know that that's not true. What's the next function you want to look at? Y equals x.
What number is this?
25. So let's do the y equal x graph. So there's the original function graph, and what I need to do now is say at some point, how about this point right here, what's the slope there?
X. Or 1. Yeah.
So my function is y equal x, and the slope right here is 1. So for this x value, I'm going to put the dot 1. How about right here? What's the slope right there?
1, 1.
And how about right here? What's the slope on the original function there? 1. And so what do I end up having? A horizontal. And so the black line was the original function. The red line is its derivative function. Is the derivative of x its own derivative?
No.
Is x its own derivative? And the answer is no. But can we do the thing that we just did there? The derivative with respect to x of the x curve equals 1. Yeah.
Does that mean any linear function that you have, it won't equal its own derivative?
Correct. As far as I know, there are only 2 functions that are their own derivative. And those are, well, one of them we're about to hit.
Yeah, and the other one?
And the other one is f of x is equal to 0.
Okay.
I mean, f of x is equal to 0. Let me graph the 0 function. Let me make it nice and thick, so you can see it on top of the axis, of course. Here's the 0 function. What's the slope here?
0.
0. What's the slope here?
0.
What's the slope here?
0.
What's the slope here?
0.
I know. So if I connect all those things, what do I end up with?
0.
The black line and the red line are exactly the same. The derivative of the 0 function is 0. It is its own derivative. But that wasn't part of the problem. So how about this next one? Square root. Where's square root? Right here? X? So it's graph. Oh, I still have it in thick graphing mode. So what do we have for its derivative? Let's talk about what happens really, really close to 0.
Isn't it 1 to 1?
I'm getting really, I'm going down, I'm getting really steep. When I have steep slope, my slopes are really high. So when I get really close to 0, I've got derivatives, I've got slopes that are way up here, probably. And then what happens as we go on?
Slope decreases. Yeah, gradual.
We got a slope gradual, and then, so what do you think happens? It's something like, maybe like that? As time marches, as x gets bigger and bigger, the slopes get more and more shallow, closer and closer to 0. So, black line is the original function, there's our derivative function. Is that its own derivative? No. All right. E to the x. Where's e to the x? Second, e to the, oops, there's natural log. I don't want natural log. Second, e to the x. There we go. Graph. So, this is the other one that is its own derivative. How can we tell? Well, what do we know, what do we see about the slopes here? 0. And where are we? Around 0. 0, 0.
It starts to go up.
Okay. Here, let me draw a tangent line right there. What does that tangent line slope look to be about? About 45 degrees?
Yeah.
About 1?
1 to 1.
Yeah.
Okay. And so, right here on that line happens to be the coordinate 0, 1. Because e to the 0 is
1.
equal to 1. And as we get further, let's see right here, does that slope looks more steep? Yeah? Maybe that slope is about, oh, I don't know, about 3. And what is this point? Over 1, and e to the 1 is, well, it's e. It's approximately 2.71 1928 something like that. I have not yet managed to memorize all the at least 10 digits of E. No, I can't do the first 3 verses of the Raven though. But that really is not a very useful skill either. All right, so e to the x ends up being its own derivative. All right, and then let's look at the last one, and that is x squared. Get rid of that thick line. Oh yeah. Kinda. Okay, so let's take the easy point. Here's a horizontal tangent. So this red dot is on the derivative graph because when x is 0, it has a horizontal tangent. Its slope is 0, so that points on there. How about here? You want to take a guess at that slope? About 2? You know what? I'm asking you to estimate it.
I say 1.
Can't we just do this? Can I just go and say second calc dx, and say I want to know what the derivative is at 2. Oh, it's 4. Oh, that's right. At
1.
At 2 it's 4, and at 1 it's went into trace mode. Second calc derivative at 1 equals? It's 2. Okay, so we've got 3 points here. 0, 0, 1, 2, and 2, 4.
Are you still figuring that?
Probably. Probably.
It's a little weird.
So that's probably not 1, that's probably half a pi. But anyway, the graph of the parabola, the graph of the derivative of the parabola ends up being a line. It ends up being the line 2x. It's not its own derivative.
Oh, duh. Oh, sorry. No, I was.
Actually, because we did this problem.
Huh?
We've done this problem. We've calculated the derivative function for x squared. It's problem number...
Oh, it's number
What is that?
13.
Problem 13?
Yeah. Because it had to match the graph of the function with the derivative.
Yeah. Or
And that was sine.
we could also go back to the definition. It ends up being x plus h squared minus x squared over h. The limit as h approaches 0, x squared plus 2xh plus h squared minus x squared over h. Boom, boom. We're going to get a little sloppy, that, and that's a 1. That goes away. When we apply the 0, we get 2x. So we actually can show that it's 2x.
So the derivative of x is 2.
That's correct.
And not all derivatives are linear, just for parabolas?
It ends up being that the derivatives of parabolas are linear. It ends up being that the derivatives of linears are constants.
Or horizontal?
And actually, we're going to learn, essentially, when we take the derivative of any polynomial, the derivative ends up being an order 1 less. So quadratics turn into linears, linears turn into constants. If it's a cubic, it turns into a quadratic. But that's for later on.
But e to the x is e to the x.
But e to the x is e to the x.
Zero.
And we're getting intuition on that right now, but later what we're going to do is prove it. All right, 29. 29? 29.
Oh, this is the,
By the way, which ones have we done so far so I can...
we did, 17 and 25.
Okay. And now you want 29, right, Evan?
Yeah, 29 is the one with like a lot of data.
Data? Okay, 29. Okay. Let's do 29 this way. Let me bring up the data right on the screen, and then we'll write right in the book. Nope, wrong one. Calculus. That's our book. PDF. And then what page is this?
107.
Give us a second. There's no page 107. No, it's
Well, maybe it's the next.
because it started numbering over again.
Oh, I gotcha.
Well, that's
Maybe because I'm in chapter 2, not chapter 3. Maybe that's
oh, that could be.
that. How about I go to chapter 3,
Yeah.
and then how about I say 107 now? How about that?
Look at that. Think about it.
Okay. So here we go. Now, here's what's going on with this. Let's go back to chapter 2, when we started talking about the relationships of the distance formulas and speed. You look worried. I don't know why you look worried. And we use expressions like average speed versus instantaneous speed. Do you remember this? Because I'm remembering this.
Yeah.
I do.
Instantaneous was just like
Tangent
what we,
and
the
secant.
Tangent.
equation is the derivative.
And the what? The instantaneous was
Tangent.
the tangent, but an average speed was a
Secant.
secant, where we actually take 2 points. Okay?
Yeah.
Yeah. Okay. So when we look at this data, and see, we got time in one column, we got distance in the other. That's telling us distance, but if we want to get at speed, we got to get something that looks more like a slope. We got to look at this, and we got to make it look more like a difference in y's over a difference of x's. So I got a great idea.
What is?
Let's talk about the speed, the average speed between those 2 moments of time.
Final minus initial.
Final minus initial, tell me more.
3.3 minus 0.
3.3 minus 0.
Then you go to 13.
Wait,
Oh,
that's a change, that's going to change
minus
over what?
0.
Over 1 minus
1.
0, which is going to be 1.
So the
It's always
speed
going to
is
be 1 in the denominator.
Okay, so we could say that the average speed between those 2 points was 3.3.
Yeah.
We agree with that?
Mhm.
Okay, what if we do that again?
10.
No, 13 minus 3, 13.3 minus 3.3.
2 is fine.
10 is the difference in these values,
10 over
divided by
2
Oh,
minus
2
1.
minus 1.
2 minus 1, that's going to be 1. Okay, so we went from 3.3 to 10.
Yeah.
All right, now what?
Same thing.
29.9 minus 13.3 over
16.9?
6.
16.6?
Yeah.
Okay,
Over 1.
over 1. I'm going to say the over 1's understood now.
Okay.
53.2 minus 29.9. That's going to be something like 23.3. Is that right? All right, and I do that again. And what do I end up getting? I'm getting an average speed of 3.3, 10. You know what? Do we see a trend with these numbers at all?
Increasing by 6.6 or 6.7.
Each one of these is increasing by about 6.6. So if I subtract these two, what do I get here? 30, is it exactly 30?
Yeah.
Okay, and did this speed go up by about 6.7 there?
Yeah.
So it seems like every single second, the speed is getting about 6.7
Larger.
larger. Okay, so what we might say, and I don't know if you can see, here's the answer, because this is the teacher's edition of the PDF.
Didn't even see that.
What they're saying is, yeah, you see that trend in all the speeds. The speeds aren't constant. They're not going up by but they are going up by a constant, which makes them predictable.
Yeah.
Yeah.
Do you think they ended up doing like a regression to get that, or do you think they actually plotted it out and then did what we're doing right here?
Well, if they did a regression, the regression would have been something like 0.5, 3.3, 1.5, 10, 2.5, 16.6. Now, I think you can see where I'm getting those numbers, right? Where am I getting these numbers?
Midpoint.
The midpoints between these two values. Because we're not saying the speed at 0 was 1. Or the speed at 0 was 3.3. And really it was the average between those. So we probably take the midpoint. So if we use these as our time, we use these as our speed, and then yeah, you could do a regression. Yeah, something like that. Those are all reasonable ways of attacking that problem. And in general, every second that we get further, the speed was increasing by about 6.6, 6.7, or somewhere in between there. And that's how we attack that problem. Yeah.
So, I don't understand what it's asking when it says the equation of the derivative. Like, it just wants to know what the slope is, like what the derivative is.
Okay. Each of these values is a slope between 2 points. And those points between 1 and 0, between 0 and 1, between 1 and 2, are relatively close together. So each of these is a good estimator of slope at a point. Not great, but we're lacking the data to get any finer than this. And because these are good estimators of that slope, the function that returns these values would be a derivative function. Not perfect, but the world in data collection isn't perfect either. So it's like, it's as precise as we can get given the data that we have and given how chunky the data is. A derivative function, okay, let's just go back, let's take back a step. A derivative function does what?
It gives you the slope.
It gives
rate of
us
change.
the slopes. It's a function that returns slopes. These numbers are slopes. A function that would give us numbers like these would be a derivative function.
So each one of those is a different slope.
Each one of these is a different slope between 2 moments in time.
So it's increasing the slope really fast.
The slope would be positive for these values of t, yeah. That would be a true statement too. Okay, let's do what, let me put this, I'll put one more in here. 3.5, what was the next one?
16,
That was 23.3. Okay.
So if you
Let's go to that regression, right? Let's do this. Let's take this data and let's find an equation that matches that regression, or the regression equation that would match that data. Stat, edit, and let me get rid of this old data. Are you guys? We have not done this in class before. Emily's been doing it in stats. Is this something you guys have done in other classes? Yes?
Yeah.
Evan?
Yes.
Kelly? I know you did it last year, Mariah, because we did this in stats. Olivia? No? No? All right, here's the idea. We have data. 0.5, 1.5, 2.5, 3.5. Oops, missed the 0.5 on that one. Come on. 2.5. Right? We had data that came from the speeds. 3.3, 10, 16.6, 23.3. Okay, and those are Y data. And the question is, what is a reasonable equation that would describe the relationship between X's and Y's? The tool to do that is under the stats menu, and it's called linear regression. Give me X and Y data and give me back a linear equation that tries to describe that relationship. So if I say 4 and hit enter, it says the linear equation that describes the relationship between my X data and my Y data has a slope of 6.66 and has a Y-intercept of about -0.2, essentially 0.
May I have your attention, please? This now concludes this year's CASA Open House. I hope you enjoyed the opportunity
So
to
the
take
slope
part
of
in
this
the learning
line
presented
is
tonight.
6.6 and
On
it's linear.
behalf of the staff
The
and myself,
derivative
I
equation
would like to thank you for attending
would
this
be
program. I want to also remind you that
6.66
cookies and refreshments
X
are available
or
at the
T,
north end of the main
because we
hall.
were really talking about time.
And finally, we hope to see you again at the parent-teacher conferences next Tuesday, October 12th. Please drive safely and have a great night.
That was invigorating.
Okay, I got to separate.